In this video, we want to continue to look at optimization and modeling problems where we have situations where we need to try to optimize by using our derivatives and our calculus, and this is part 2 of this section. So the first example I want to look at is find a point on the parabola 1/2 x squared that is the closest to the point 4, 1. So 1, 2, 3, 4. So 4, 1 is a point right there. And we want to find where is the point on this parabola closest to that point. So that is going to be some point right here on that parabola that distance is the closest. And that point is going to be the point x 1/2 x squared. So wherever that x is, whatever this x is, it looks like it's maybe close to 2, but wherever that x is, the y coordinate will be 1/2 x squared because that is our function. So the way that we want to find this distance that we're trying to minimize between these two is we're going to use the distance formula. So the distance formula is the square root of x minus 4 squared. Right, this is the point x, 1/2 x squared. This is the point 4, 1. Plus 1/2 x squared minus 1 squared. Now, one of the things we're going to do to help us, because as soon as you look at that, you think, I do not want to take the derivative of that. But if we are looking for the shortest distance, distance is positive. If we looked for the shortest distance squared, that would be the exact same thing. And what that does for us is that changes our equation to just this polynomial. We can get rid of that square root and make everything easier. So instead of just finding the distance, we're going to find the distance squared. So if we now want to find the distance squared's derivative, that would be bring down the 2, subtract 1, times the derivative of the inside, which is the same. And yes, we could multiply this all out, but it's easier, I think, just to use the chain rule here. So the second part, we bring down the 2, the inside stays the same. We subtract 1 times the derivative of the inside, which if I bring down the 2 is just x. So if I simplify this, this is 2x minus 8 plus 2 times the half cancels. This is x squared minus 2 times x. So really this becomes x, this becomes cubed. So this becomes x cubed minus 8 as these two parts cancel out. So that tells me my critical points on the derivative of the distance squared is the cube root of 8. So that tells me my critical points are 2. Now, once again, I need to show this is a minimum. So I could do the first derivative test with sign analysis, or I could do the second derivative test. I'm going to do the second derivative test. So if I take the second derivative of this, I get 3x squared. But that is always positive. And since that's always positive, that tells me that is a minimum. So from over here, my x coordinate is 2. And then if you put 2 in there, 1/2 times 2 squared is 2. So from the graph, it looks like it's 2, 2. And then we just did the calculus to confirm that the closest point to the parabola from 4, 1 is the point 2, 2. So another example. A little more complicated here using some angles and some trig. The movie screen on a wall is 20 feet high, 10 feet above the floor. At what distance x from the front of the room should you position yourself so the viewing angle of the movie screen is as large as possible? So how far back should we go so that this theta is as large as possible, and we're trying to find this x that gives us the largest angle? Now, the first thing I'm going to do is I'm going to say, okay, we have this angle here, which I'm going to call alpha. So we have two right triangles here. The smaller right triangle tells us that the tangent of alpha is 10 over x. The second triangle tells us that the tangent of theta plus alpha is 30 over x. Now remember, the angle we're trying to solve for, the angle we're trying to look for is this theta. So we want to get rid of the alpha. So we're going to use our inverse tangents here. So we'll say that alpha is equal to the inverse tangent of 10 over x. And theta plus alpha is the inverse tangent of 30 over x. One of the reasons we've talked about taking the derivative of inverse tangent so much is because anytime we have these kind of problems that we have trig functions, we can always write things as tangents and sines, solve for angles, and then you end up taking derivatives of inverse sines and inverse tangents. Now, we want to find just theta. So what I'm going to do is I'm going to take this whole value here, which is alpha, substitute it into here, and then I'm going to subtract it to the other side, which will give me my equation for theta is equal to the inverse tangent of 30 over x minus the inverse tangent of 10 over x. And I now have my equation for theta that I can maximize based on x. So the first thing we need to do is we need to take the derivative. So the derivative here is the derivative of inverse tangent is 1 over 1 plus 30 over x squared times the derivative of the inside, which is 30 over x, which is negative 30 over x squared. Do the same thing with inverse tangent of 10 over x, and that's 1 over 1 plus 10 over x squared times negative 10 over x squared. And just write it out and go with it. We'll see what happens here. It's getting long and nasty. So if we simplify that here and we multiply through, we get this negative 30 on top. And let's see what happens to the bottom. This is x squared is going to cancel with this x squared and just give me 30 squared, which is 900. And this x squared is going to multiply by 1, so I get negative 30 over x squared plus 900. I'm going to do the same thing over here. This is going to give me negative, and negative is going to give me a 10 on the top. This x squared here times 1 is x squared. When I distribute it to here, it's going to cancel here and just give me plus 100. So there is our derivative. Now, if we want to find the critical points, we need to determine where this is equal to 0 and solve. And to do that, we have to get common denominators. So I'm going to multiply over here by x squared plus 900 over x squared plus 900. And over here, x squared plus 100 over x squared plus 100. Now, if we distribute this to both of those, we distribute this to both of those. I have this written down already. What that is going to give me is minus 30x squared minus 3,000 plus 10x squared plus 9,000. So that is, going back here, so again, that's negative 30 times x squared. Negative 30 times 100 is negative 3,000. And 10 times 900 is 9,000 and 10x squared. And then our denominator is just x squared plus 900 and x squared plus 100. And then we want to determine when is that 0. Now, our denominator is always positive. So that's something I'm not even going to multiply it out. I'm not even going to rewrite it. On the top, we get minus 20x squared plus 6,000, which if we continue, if I factor out the 20, I have x squared minus 300 all over the bottom, which once again is always positive, so I'm not going to worry about it. So my critical point is plus or minus the square root of 300. But once again, we are dealing with the distance from the screen, our x down here, so we only deal with the positive. Okay. Now, I'm going to do sign analysis. So I'm going to do sign analysis. Once again, we can't go below 0. The square root of 300. Now, as we do sign analysis, we're going to go back to here. And remember, the bottom's always positive. Okay. The top's always negative. So if we look at the top right here, let's think of what this quadratic is right here, right? If we were thinking of this quadratic, let me come over here to the side. If we're thinking of this quadratic, that's all that matters. The bottom's positive. And we were to graph that, we know positive, negative, square root of 300. This is going to go something like that. We are only dealing with greater than 0. So we know it's positive here, negative there, which tells us this is positive, negative, which tells us this is a max. So we know our maximum viewing angle is when x is equal to the square root of 300, which is about 17.32. Now, what if you wanted to actually know what the maximum angle was? If you wanted to know what the maximum angle was, to actually find theta, you have to come back to here. And you need to plug that x in. And we could do that on a calculator and say inverse tangent of 30 divided by 17.32 minus inverse tangent, not that messed up there, inverse tangent of 30 divided by, let's do the square root, we'll even make it more accurate, square root of 300 minus inverse tangent of 10 divided by square root of 300. This will give us our theta, which is 0.52358. So if we go back to here, this is the formula I used right here with x. So what is our maximum angle? It's kind of hard to tell in the decimals, but if we go think unit circle values, we do know that pi over 6 is that answer. So given this, at what distance would the viewing angle of the screen be as large as possible? Our answer here for x is the square root of 300, and that's actually what the answer is. But if we're curious what that does for the angle, the maximum viewing angle is pi over 6. Now, once again, once you got to this formula, that's just a formula. We could just graph that in our calculator. We could just graph that, make sure in radians. We should graph that and then find the maximum. But what happens if we can't just graph it? What happens if we don't have the variables to graph it? So let me show you what I mean. The range of a projectile with initial velocity of v sub 0 at an angle of theta with the horizon is given by this formula, where g is the acceleration due to gravity. Find the angle theta to maximize the range. So now you'll notice our formula, we don't even have any numbers or variables. We can't graph this, but we can still, based on these variables that represent the angle, that represent our initial velocity, that represent our acceleration due to gravity, we can find the angle based on all of those things. So to do that, first thing, we need to find the derivative. Now, I want you to think of this r in a little different form. V sub 0 is our initial velocity. That's a constant. G is our acceleration due to gravity. That is a constant. So really, our function is a constant times sine. So if I want to find the derivative of that, the v sub 0 squared g just kind of hangs out in front, and then we get cosine of 2 theta times 2. Now, we want to determine where that's 0. Now, this 2 doesn't really affect that. This is really just 2 times v sub 0 squared g cosine of 2 theta. So, where is that equal to 0? Which really means where is cosine equal to 0? And if you think about our unit circle a second, this is the easiest way to think about this because it's 0. Cosines the x are 0 is at 90 degrees, or pi over 2. But this is actually 2 times theta, so my critical point, I divide by 2, is pi over 4. So from this, it is looking like our maximum range is at an angle pi over 4, 45 degrees. Makes sense. But we still need to show that this is a maximum. We just found the critical point. We have to show it's a maximum. Maybe it's a minimum, and maybe our formula and our problem is not correct. So we know it has to be a maximum. So to do that, I'm going to use the second derivative test, which the derivative of cosine is negative sine times the derivative of the inside is a 2, so it kicks out a 2, so this constant in front just becomes 4 v sub 0 squared over g. And if I plug pi over 4 into there, that's sine of 90, which is 1. But then with this negative right here, this is less than 0. So we have a max at theta is pi over 4. Now, that's 100% intuitive. If you were going to shoot off a rocket with projectile motion, the range that you would probably guess, if you were going to get the best range, right, would be at 45 degrees. If it's higher than that, it's going to go up and not out. right? If it's lower than that, it's not going to get a long enough distance before it hits the ground. That intuitively makes sense, and our math works out to confirm that. Okay. So these are the kind of problems you're going to have to work on the second part of the homework, where you have no variables, you have no numbers, so to speak, that you can graph it. You just want to find the derivative. We'll look at one more this talks about in the book. We're not going to look in the book to find this, but I just want to point out a few things as you look at these kind of problems. So this has to do with the velocity of coughing and how fast air is coming out of the throat. R has to do with the radius of the trachea, and this gives us our formula for the volume. So I'm not going to get into what that more specifics of that. Here is our formula. One of the things you want to think about as you start this and you want to find your derivative is, what are your variables? What's the variable you were taking the derivative of? It talks about in the problem, C is just some constant. Just a number. We don't know what it is, but it's some constant that depends on everybody's personal physical size and shape. R sub 0 in the problem is called the resting radius of the throat. So once again, some constant, we don't know it, we're looking at a generalization. So R is the variable that we are taking derivative of. Now, one of the things I can do here to kind of make this a little easier is I'm going to distribute this C and distribute this R squared to kind of make this look like a parabola, so, or a polynomial. So this would be C R sub 0 R squared minus C R cubed. So now, as we take the derivative, bring down the 2, this would be 2. Remember, C and R sub 0 are just constants, minus R, minus 3C R squared. Now, if we factor this, we can factor out the C and the R. So this is going to give me C times R is 2R sub 0 minus 3R. So now, if we find our critical points, there's really 2 critical points. This first part would give us 0. And this second part, if we set that equal to 0, would give us 2/3 R sub 0. So these are our 2 critical points. Now, we intuitively, if you remember, R is the radius. So this 0 intuitively is going to be a minimum. What is the velocity of the air coming out of your throat when the radius of your throat is 0? When your throat's completely closed off, you have no air coming through. That's a minimum. So what we need to do is show that this value gives us a maximum. So the way we could do that, I would do second derivative test. My second derivative is 2CR0 minus 6CR. You can see now the only variable is right here, so I want to substitute in R right there. So I get 2CR0 minus 6C 2R0 over 3, which is going to give me, this cancels, let me switch colors. This cancels here and gives me 2. So I have 2CR0 minus 4CR0. So this is going to give me negative 2CR0, which is less than 0, which tells me less than 0 tells me this is a max. So I've just shown that that value is a maximum. All right, you are now ready to do the optimization problems, part 2.